the same result, right? So that case also works out fine. If beta equals to 0, what do you think should be the result? Sorry? Huh?
Don't have a scrubber?
Again, you don't have a scrubber, so that result will not come out from this equation. Because if beta equals to 0, you have no scrubber, but the expression for cost is not valid when there is no scrubber, right? And so that again expression will not come out from this equation directly. Make sense? Okay, so now let's put some numbers and see what we actually get. So we actually, the good thing is that we have reasonable numbers for most of them. So we know CS is 25 ppm, right? Let's say Cmax is 150 ppm and Cmin is 100 ppm. Okay, which are all quite realistic numbers. So then the only question left, of course, is what is the ratio of beta to alpha? So let's say, so let's just put those numbers in and see what you get. So you get alpha times Cmax minus Cmin, which is 50. So you get 50 alpha divided by Cmax, which is 150. So 150 minus delta C divided by 100 minus delta C equals to beta times Cmax, which is 150. So 150 minus CS is 125, so 125 minus delta C. Right? So that's why you can see why the equation is a cubic equation. All right, so now, of course, you can solve the equation by saying that for 150 minus delta C times 100 minus delta C times 125 minus delta C equals to 50 times alpha over beta. And so it's a cubic equation. Do you guys have calculators to solve cubic equations?
You told us not to use them.
I tell you not to use them for the quiz and exam.
Can we use them now?
So can you use this? So let's choose alpha over beta. So we'll choose a few different values of alpha over beta. So let's choose alpha over, so let's choose, so beta is the penalty, right? So okay, let's choose alpha over beta to be 1, alpha over beta to be 0.01, and alpha over beta to be 100.
So if it's a cubic, which one?
Okay, good question. So cubic, so how many roots will you get?
3.
3. Which one will you take?
From 0 to, no, from 1.
So if an equation has 3 roots, what can you say about those 3 roots?
2 of them don't make sense.
Sorry? But what can you say about the other 2 roots? Let's say one of them is complex. Most likely 2 of those would be complex. Or maybe not. But if an equation has a complex, if an equation with real coefficients has a complex root, what can you say about the other root? The other one has to be complex conjugate. So if 3 are real, then the 3 will be real. But if 1 is real, 1 is complex, and the third one will be complex conjugate.
Even if all 3 are real, you have bounds on like what you expect your upright center.
Right, so more than likely only one of them will make physical sense. Yeah, you'll see only one of them will be a positive number.
That's what I said.
They're all three positive numbers.
They'll all be positive numbers. For which case?
For case 1, I get 99.96,
Okay.
125.08, and 149.95.
So you can see basically what it is that because 50 alpha or beta is sort of a small quantity compared to all these numbers, therefore one of these numbers has to be small. So they all three basically are bordering 100 or 125 or 150, right? So now of course we can make our physical arguments that say that delta C should never be moved. So C, let's look at C max minus C. So C max minus, so C max minus C safety is 150 minus 125. So you will never have that number larger than 125, right? Make sense? So therefore you can discount these two. That's your answer. Okay. All right. So what about 0.01?
99.99, 125, 149.99.
So for the same reason, you'll again basically choose this, right? Okay. What about this?
96.68, 134.27, 144.03.
144 point.
03.
So again, you'll obviously choose this.
So let's pick the lowest one.
No, not the lowest one. We are picking it because we know that a solution, the correct solution, should never be larger than C max minus CS because that makes no sense.
Oh.
So C max minus CS is 125. So we know a solution should never be larger than 125. So we picked the only solution that makes physical sense. Okay.
If there are multiple ones.
Yeah, what do you do?
Sorry?
If there are multiple ones that are 125, then you want to take those.
They will not, it's unlikely because the mathematics always works out in a way that you should be able to rationalize. Then you have to start thinking why? Why are there two solutions? Does it mean there are multiple local minimums, in which case you have to go back and see not just the lower value of the CS, but at what value of CS is the cost, total cost lower, right? But in any case, this time it's quite nice.
So, thinking about this, like, what is the representation of alpha over beta? Are we saying like the cost?
It's basically alpha or beta is the cost of, yeah. So alpha is the cost of scrubbing. So that represents the cost of scrubbing versus cost of the penalty. However, remember the problem is that alpha and beta have different units. Right? So yes, alpha or beta does have that meaning. But if you really want to get a little bit more clear about this, you have to do this problem in a dimensionless form. So that you can have a dimensionless ratio which has usually more meaning. Dimensionless numbers is very difficult to say, put meanings to them. But yeah, basically that's what it is. Okay. Now you notice they're all close to 100. They're all close to 100 because in some sense, the cost of your scrubbing, the formula that we're using for cost of scrubbing becomes very flat. So what it is, and that's why I told you that's sort of the weakness of this problem, of this analysis. The cost of scrubbing, we are saying is 1 over, goes with 1 over this, right? So it changes a lot in this range, but in this range it doesn't change by much. It's basically very, very flat. So the cost is not changing by much. So basically what you have to make sure is, make sure you don't pay the penalty, right? And so therefore it's coming close to that 125. If it's at 125, you'll never pay the penalty. Okay. All right. Make sense? All right, good. So, this problem, as I told you, this problem I kind of constructed out of my own experience. So I don't know if that was useful to you or it made it more complex. In some sense, it's a little bit more complex than I think a number of problems that I could have done. But I thought this would be more meaningful because it is actually a real problem. Okay, now I'm going to do another problem of optimization. So right now is, we started the course talking about essentially figuring out whether the problems that you're looking at are economically good or not, right? And then we said, well, you know what, that's great, we have all this method of figuring that out, but there's inherent uncertainty in parameters, and how do we take care of that, right? And so we said the way to take care of that is to look at probability distribution function and integrate whatever we are interested in over the distribution, and then use that to figure out whatever answers you want to deduce, right? So we can do that in terms of NPV. But then now we are going to slightly different types of problems, which are still, you're still trying to minimize the cost, okay? But in this case, the cost minimization is coming from optimization of the cost itself, not from the return on the cost. Okay? So you can see in this case, we didn't talk about how much money we're going to make or not. Because anytime you want to, of course, make money, maximum money on a problem, the first thing you want to do is you want to optimize the design itself. Right? And then you want to look over long term whether you see with that optimized design are you making money or not. Does it make sense? So now in the second part of the course, we're stepping away from that economic analysis. We are still doing economic analysis, but we are saying in order to really make most money, we have to first design each and every process so that it is already optimized. Okay? So we're still doing cost optimizations, but we are doing it in the context of designing different equipment, because that is a necessary requirement in order to, of course, do the overall economic optimization. Right? You can always make more money if you design each equipment and the entire plant in a more optimized way. Does it make sense? Okay. So this was one example of that. Let me now do an example which actually you all might be very familiar with because you are taking reaction kinetics. So in reaction kinetics,